Welcome everyone to the 14th video in a series of videos on solar and wind energy estimation and forecasting application developed in MATLAB. I'm Kiran Gaikwad, the developer of the application. I have a Master's of Technology in Power Electronics and Power Systems from Sardar Patel College of Engineering, Mumbai. I'm currently working as a Junior Project Fellow at GERMI, Gujarat Energy Research and Management Institute, under Dr. Sardar Agrawal. In this video, we will have a demo on the ARIMA forecasting application. And as we all know from the previous videos that the ARIMA forecasting application is a part of the forecasting application which has been developed in MATLAB. And as you can see, this is the main interface of the forecasting application. And in order to start the ARIMA forecasting app, we can press this button. Okay, we'll minimize this. And this is the first GUI in a series of GUIs which we would look forward as we go through the workflow. And this is the ARIMA data acquisition app. The main function of this app is to acquire the univariate data series on which we will do ARIMA forecasting. So we have three kinds of series which we can handle. One is where the user doesn't have any series and he just wants to create an ARIMA model and simulate the model when he has the coefficients of the ARIMA model with him. The second one is data without date and time signature, and the third one is the data with date time signature. For our demo, we will use a data series which has a date time signature to it. We can select this one and we can say get data. Now we have to load that file, and this file would be in a Excel format. And we have to find a file in our directory, and that's somewhere here. Okay, so now it will process and we will have the total number of rows and total number of columns within data file, and I'll show you the structure of this data file. Actually, I have it here, and this is how the input file looks like. And this is a 1 month's data, June 2016 weather variable data of a particular location, and this is the day column, month, year, time in decimal, wind speed in meter per second, temperature in degrees Celsius, meridians in meter, watts per meter square. Okay, and this is the file which we have now just now loaded into the application, and let's go forward. Okay, so we know that this file has 2880 rows and 7 columns, and as we can see, we have to enter values. If we would have selected data without date and time, these fields would have been enabled and these fields would have been disabled, but as we have selected data with date and time, we have to enter some more information, and the series number inside that for irradiance, as we saw, was 3. This is the third data series. Other things are the date and time signature. Okay, so let us see. Series number is 3. The resolution of the file is 15 minutes. The year is 2016. Stop is 2016. June from how much, like we have to slice the data right now, and we don't want to use the entire 1 month's data for our prediction model. So what we will do is we will slice the model, and from that 29 days worth, 30 days worth of data, we are slicing it to have first 4 days, and from 12 in the midnight till 10 in the morning of the 4th of June 2016. So this is how we will slice that data and have the piece of data, univariate data series, which we will be working on in the further windows, and this will be sliced using the data acquisition app. And this can be done by just pressing OK. And once this is done, we will have to go to the next tab, because now we have acquired the data which we require. So let's go to the next tab. This is the model identification app. Over here, we will try to identify what kind of ARIMA family model would best fit our data. So we can first start checking for stationarity and press this button over here to plot the original data series, and this is how it looks. It's quite even. Actually, these are the 4 days. This is the first, second, third, and the fourth day up till 10 o'clock. And we have these many observations. This is the original data series. So we can check whether this data series is it stationary by using the Dickey-Fuller test. For the original series, we press over here as the result is 0, so it fails. That means this series is not stationary, so we have to make it stationary. So we can do that by detrending it. So we can detrend it by using single lags or seasonal lags. So I know that this series has both single as well as seasonal lags. So we'll use single lag number 2 and seasonal lag number 96, as there are 96 values in each day, as we have a resolution of 15 minutes, and we can plot the lag operated data series. And as we can see, this is more of a Gaussian noise kind of a representation as compared to this one. But is it still stationary? So we can do a Dickey-Fuller test on the lagged series, and yes, as the result is 1, the new lagged series which we have detrended is stationary. So now we can go forward and we can look at the ACF and PACF, that is the autocorrelation and partial autocorrelation functions, and we will plot them. Okay, so now using the junk box test, we can see which lags are worth using. So let us input the lags. Sorry, so lag 1, 2, lag 3, lag 4, lag 5. We'll say we'll press the junk box test button, and all these are significant lags. Okay, so the series depends upon all these lags as well. But now we will check for the dependence on the PACF test and the PACF series, how many lags in the PACF are significant. And what do we get? No thing is significant, but it is not correct actually. We will try to plot it with 100 and see what happens. Plot them again, so we have more lags now. Okay, there's some kind of a tweak we have to make, because I have tested this data and I know that it is significant, and we were able to see that it was significant. And as we can see in the PACF, the first 2 lags are significant. The other 3 from these are not significant. Okay, so we can use this knowledge about our ACF and PACF to model or create models of the ARIMA family. Okay, so what we have as our information is that the ACF has the first 5 lags which are significant, and the PACF of the detrended data series, the first 2 lags of the PACF are significant. So we have enough information about it. What we have done in this window is that we had a look of our sliced data series. This is the original one, and we checked it for its stationarity. It wasn't stationary, so we tried to detrend it and convert it to a stationary series. We did that using the lags. We used both single and seasonal lags, and then we tested the lag operated series, and it gave us the result of 1 using the Dickey-Fuller test, which means it is stationary. Then we checked the ACF and PACF plots for the detrended lag operated series and tried to see how many lags are significant using the junk box text. So using this information we can go forward. We will press OK so that the detrended lag operated series is carried forward, and we will go to the next step. Now the next step is to create ARIMA models. So we can create n number of ARIMA models, and we will create two for this demo. And what kind of model is it? Do we know the parameters of this model? No, we don't. We don't know the coefficients. So this is an unknown model. And then we have all these options. So the first one is we will have normal PDQ type of a model, and we will enable the following fields for this. And as we can see, we have many fields, but for this kind of a model, that is PDQ, we can create an ARIMA model using just these values. So I have selected, or I have entered value 2 in the P part, which is the autoregressive part of the ARIMA series, as the PSCF had two significant lags. D is equated to 2, as this is the integrating part, and as we have used single lag number 2, we have to use 2, and as we have seen that the ACF of the detrended series has 5 significant lags, I have put in 5, and then we can create the model. Then we can display the model in this area, and we can see have we created the correct model or no, and then we can go and select which kind of model we have to create next. So I have to create a model which depends upon lags, and it will depend upon both AR and ML lags. Is it seasonal or non-seasonal? Yes, it will be seasonal. It will have both SAR and SMA lags, and then I will enable the appropriate parameter fields by pressing this, and you can see that different kinds of fields have popped in or have been enabled now. So D is 2, AR lags is 1, 2 for the autoregressive part. For MA part is 1, 2, 3, 4, 5. As we have seen, the ACF and PSCF, the seasonality of this data series is 96, SAR will be 96, SMA would be 96, and constant we will keep it as 0 over here. We will create the model, and we will display the model, and this is the model which we have over here, and whatever we are using over here is represented in a proper format in this text box. So we can display all the models as we have completed creating the two models which we wanted to create, and we can see them. Okay, now we can just press OK so that these models are transferred to the next window, and then we can go towards estimation or simulation. But simulation window would be used only when we know the coefficients of the ARIMA models which we create, but we have created unknown models, so we will go for estimation. And now how many this is the GUI for the model estimation app, and as we see we have to enter certain values which are number of ARIMA models created. This is 2. Then we will have to enter the number of lags we want to see of the ACF and PACF of the residuals which would be plotted over here, and we can just say estimate ARIMA models, and it will take some time to populate these graphs. So in this app we will estimate the performance of the ARIMA family models which we have created in the last GUI, that is the model creation app. And what this thing is doing right now, it is trying to compute the coefficients of the ARIMA family equations and then give us the appropriate graphs so that we can make a decision on which ARIMA family model should we take further for using it in our forecasting or prediction GUI. So it is taking some time. We have to wait for a while. check what's going on. Okay. It is computing. These are the constants which are being computed. It will take some time. Let's wait. And it will also represent or calculate the AIC and the BIC values, which are nothing but acolyte information criterion and Bayesian information criterion, and the model which has the lowest AIC and BIC values among the different models which are trained for the same data. The model with the lowest values of AIC and BIC is the best fit for that particular data set. Okay, so we are having this, and this is the ARIMA model estimate viewer, where we can see the computed coefficients of the ARIMA models we have created in the last GUI. And this is how it looks. We can just close it and concentrate on the graphs. So we can see a QQ plot over here. Over here we see the standardized residuals plot. Over here we have autocorrelation and partial correlation function plots for the residuals of the estimated models, and this is how the residuals look like, standardized residuals look like. So this is all these graphs correspond to model number 1, but what about model number 2? So we can just press next, and the graphs will be populated with the values for model 2. And let us go to model 1 using this button, and we can see the AIC and BIC values as positive numbers over here, and in model 2 we have them as negative. So model 2 is better as it has lower AIC and BIC values as compared to model 1. And even when we look at the residuals, this is more Gaussian than this one, as this has some pattern in it. It's still not entirely random. So this is how you can check for which model is better, and we can go forward and we can enter, and the best model over here is model 2, and we can see the number over here, and we can just say OK, and we can move on to the next tab. Now, this is the model forecasting app over here, and we have to select whether our data is with time or without time, but our data was with time, date time signatures, and see that some fields have been disabled and some fields have been enabled. We have to enter the resolution, the year, start and stop, then the month, that is June, day, that is 4, end day is 5, time is from 10 to 10, and we can forecast. So what we have done right now is, like, we have set up a simulation period for which we have to predict. So before, the amount of data which we took was from 1st June to 4th of June, and now we are going to predict for 4th and 5th of June from 10 a.m. onwards. So we will just hit forecast, and what we will expect is to have a graph populated over here, which is this, and the red part is the forecasted value, and as we can see, it is following the pattern over here. And also we will have a should have created Excel file, but okay, this is how it creates. The forecasting has been done, and we can observe that this is following the pattern. And let's see what could have happened if we would have used the first one. like the model estimation, if we put 1 over here, which was not that good of a fit, and press OK, and then press next tab, and then just say date and time. We have 15, year is 2016, 2016, June, June 4, 5, 10 to 24-hour period, and we will say forecast. Now we can see that it is not following because it was that kind of just a PDQ model without any seasonal um, specifications to it. Is not able to predict the model. So the better model was the model number 2, which had the seasonal SMA and SAR specifications given to it. Okay. Okay. We can start the process all over again. This is like in a loop, and I can close this one. And as we have seen the forecasting, we can do forecasting using ARIMA. And I would like to show you actually reset and close the windows, and I would like to show you what this is the kind of output file which we expect out from the forecasted values. So this is how it will look over here from 4 to 5. This this will be produced by the application, and what we have done is that we can observe how good the application has forecasted. And this is the irradiance, and it is almost overlapping. The orange one is the irradiance, actual irradiance which has been used, and the blue one, which is overlapped by the orange one, is the ARIMA calculated or computed irradiance. And this is over here we have energy which has been estimated using the irradiance input to the solar energy estimation app, and we can see that there is very close relation, very close approximation to the actual energy which is in orange and the blue energy which has been forecasted using ARIMA. Okay, so this is what I have to show, and I can go back over here. And what I would like to add is that this application is useful for data acquisition and data slicing, model identification using stationarity, ACF, PACF concepts, then creating apps, creating ARIMA models of all the available options from MATLAB Econometrics Toolbox, model estimation and fitness check using normalized residuals, PACF, ACF of the residuals, and AIC, BIC values, and finally model forecasting and storing forecasted values in Excel sheet. Thank you.